Hi, Alex here. Continuing with our tutorials. The presentation that we'll be covering today is how to master secrets of asynchronous programming. And because this arcane craft is quite complex, I had no choice but to break it into several parts just to make sure we don't become too boring. There's lots to cover, and this area called asynchronous programming is quite mystified, and today I want to try and get to the point where we can understand what it is, what are the advantages and disadvantages. So I'll take it slow and easy, and hopefully we'll get to the full understanding of this very important but also very tricky area of software development. So first I'd like to talk a little bit about history, because I'm a history buff, and I believe that in order to understand something and master it, you need to fully understand its history. Otherwise there'll be some gaping holes and sooner or later come back to bite us. So we see today, this is a year 2017, that for more than 40 years we collectively have become really accustomed to writing programs that are based on the concept called central processing unit, or CPU, and we're relying on this CPU to process our code that we write. So seems like to many of us this is the only way to program, but is it really so? And going back into the history of computing, we can find some really interesting details and some differences from how we think today. So, of course, today when we think about programming, most people think of sequential programming. But back in 1968, Donald Knuth introduced a concept called network of processing units, PU. This is very important to understand the difference between current computing architecture and the one that was proposed almost 50 years ago. The difference is that in the Donald Knuth's model, there was no single center processing unit, while today we have a CPU center processing unit. Back then, this system was called mesh computing. And you can look it up, it's very interesting. I won't go into the details, but you can find very enlightening and elucidating demonstrations of that mesh computing. It never gained wide adoption, and the reason was, I think back then, it was prohibitively expensive. The computing hardware back in the 60s was very expensive, unlike today when it's dirt cheap. And because of that, because of the economy of scales and the increasing affordability of massive computing infrastructure in the cloud and etc., this mesh computing could become mainstream soon. It's hard to tell, but I have a hunch it might come back. Going a bit further, like 12 years later, a company called Ericsson Telecommunications developed a programming language called Erlang, which is short for kind of a coin phrase, Ericsson and language. So why is Erlang significant? Well, today it is in wide use by very prominent players, especially companies like Amazon, Facebook, WhatsApp. They use Erlang. And the question is why? What's so special about Erlang? The reason it is very popular among some of the heavy hitters and really top shelf players is because, as we'll see, it shares some of the fundamental concepts of mesh computing. And then once we know that, we can ask ourselves, so what is so special about this mesh computing that makes it so attractive to those companies that really want to implement and deliver high availability, high volume services. So my confession is that this presentation that I prepared here actually borrows a lot of the insights that I've gained from studying Erlang. And in case there's some questions and something is not clear, maybe, if you want to delve a bit further, maybe go and start looking to Erlang, the programming language. All right, that's all fine. But first, let's talk a little bit about imperative programming. Everybody's heard of that term. This is usually associated with the algorithmic programming. And basically, as we all know, this imperative programming or algorithmic programming consists of a sequence of discrete steps. So it's called sequential composition. We have a process that we want to implement, and it consists of a number of steps that follow each other. It is also based on the idea of continuous execution. The execution never gets interrupted. It just goes from, starts from one end and goes all the way down to the bottom, to the end of the execution. An example would be a program that will sort a collection of items. Let's say there's a data structure, contains some items, such as a list, and it's randomized, or we don't know what order is it in, so we want to write a program that will sort the items in that collection in whatever order, alphabetical or by magnitude and whatnot. So we could do that using various algorithms. There's a choice of different merge sorts, insertion sort, bubble sort, quicksort, heap sort, counting sort, etc. So regardless of the algorithm we would be using, the code that we end up implementing will always be based on the same assumption. And this assumption is basically that we are capable of pressing a pause button before we start sorting. So we get this collection of items, we pause everything, freeze any other processing, and then everything else waits until our program is done with sorting. So this is the underlying assumption. Often it's tacit. We don't express it anywhere, but you just go about doing this sorting processing by assuming that everything else is holding and waiting for us to be finished. So in this model, when we are done with processing, then we assume we are unpausing or unfreezing everything, and then we allow the world to now continue its processing and take it from where we press the pause button. This model is called imperative because we are commanding the world how to behave, like we're some perky little emperors, like we have this superpower, like a Napoleon or somebody who is just a totalitarian ruler and it's just, okay, now everybody stop, now everybody dance. Needless to say, this is a very naive assumption because it does not reflect how reality works. And of course, there's different things that can give us unrealistic expectations, but sooner or later, reality check comes to bite us. In real life, it is quite rare that to see any process waiting for any other process to finish. That's very unlikely. Because in real life, things happen to go in parallel. There's one process over here, another process over there, and many other ones we can observe, and they're all happening at the same time. Nobody's waiting on anybody else. So that's the reality. And so when we put things on paper and we want to formalize, on the left-hand side, we think our process is orderly, number of steps, but in reality, it's a spiraling downwards or upwards, crazy, chaotic world going on, and it's very hard to tame it. So I would say that the fundamental characteristics of reality is that it is process-driven. And this is some kind of a mesh, again, that we can hypothetically throw in a diagram. We have many processes, and they all kind of, interact with each other, call each other, depend on each other, etc. But it's a heterarchical system, not hierarchical necessarily. And that is what makes it hard to really tame that. because it's almost chaotic. And on our end, as programmers and software engineers, our job is to model the reality, because we are trying to automate something that is happening in the real world. We're representing it in our code, and we're modeling it. And another important thing to mention here, by modeling we actually mean simplifying, because the world, any situation is exceedingly complex. We cannot address every little detail. The only way we can get to implement something is to simplify things. And if we are modeling real world processes by assuming that there is a possibility to pause other processes, this is what we call the act of oversimplifying. So simplifying is good, but now we are oversimplifying. And one example of oversimplification will be if somebody says, so how do I, in English language, how can I make sure that I say a plural of some noun, and to claim that just adding an S to the end of the word gets you the plural is oversimplification of the English language, because while many words do have S as a plural, many don't. And Albert Einstein also said that we should make everything as simple as possible, but not simpler. So again, he was warning against oversimplification. Now, even though oversimplification is a slippery slope, we can still talk about when is it okay to oversimplify. Basically, I would say that if we're modeling some set of processes that are entirely located and operate inside a single block of computer memory or RAM, so it's located in one place, then we can maybe afford a simplistic implementation. But if the implementation is more complex, then we need to be careful and avoid oversimplification, because we are modeling by using abstractions, and basically the role of the abstraction, or the very essence of the abstraction, is it has the power to eliminate certain aspects of reality that it deems not important at this point. So when we abstract something, we're eliminating some details. We're getting rid of some details and treat them as noise, not as signal. We end up with the abstraction which we hope is a 100% clear signal. So we are modeling something, we're creating abstractions by actually taking some concerns about the situation and abstracting them away, saying we can afford to ignore them, these are not important. And often we say we can safely ignore such and such, because whether we consider it or not, that doesn't make much difference, so it's just noise, and it will just be bloat, and it will slow us down. So okay, you can safely ignore these things, but these things over there you cannot safely ignore. These are part of the abstract model that we are working on. So oftentimes good designers, good architects and software developers and engineers put their ignore mode on like a cat, and just focus on things. If you observe the cat, just focus on things it is of its interest, and you can call it and whatnot. It just ignores you off most of the time. So in a way, when we look at it this way, we say that abstraction boils down to simplification. And Leonardo da Vinci said that simplicity is the ultimate sophistication. Alan Perlis said that simplicity does not precede complexity but follows it. So that's also a significant statement. And that means that simplicity is not an easy thing to achieve. So this will be the end of part 1, where we talked about modeling abstractions and processes, parallel and sequential. And this sets the stage for part 2, where we're going to look more closely into the importance of knowing why and when to abandon continuous execution and switch over to parallel. So until next time, I hope this wasn't too confusing for you, and I will continue with elucidating the details that should explain when and why to use asynchronous and concurrent processing. Okay, bye.